This is Professor Dare of Science. This Java tutorial shows how to use recursion to calculate Fibonacci numbers. Fibonacci numbers are the numbers in the Fibonacci sequence. The sequence is shown here, these numbers 0, 1, 1, 2, 3, 5, etc. The pattern is that after the first two, every number is the sum of the previous two. 1 is the sum of 0 and 1, 2 the sum of 1 and 1, 3 the sum of 1 and 2, 5 the sum of 2 and 3, etc. And some interesting things to note here as a sidebar for the Fibonacci numbers is that if you look at the ratio of consecutive terms, 2 divided by 1, 3 divided by 2, 5 over 3, 8 over 5. If you look at that sequence of ratios, that sequence approaches what's called the golden ratio, and that is a number in mathematics called phi, which equals to 1 plus the square root of 5, that sum divided by 2. The golden ratio appears frequently in nature and in architecture. The Fibonacci sequence is very easily solved with recursion because of this general case pattern that it has here. If we represent a given index number as a capital F, then it is the sum of the Fibonacci numbers of the preceding two. So F at n is f at n minus 1 plus f at n minus 2. That's our general case. We can take and call the function itself passing a smaller number, a simpler problem. And this is interesting here because in our general case there are two calls to itself in each call of the general case. That will cause the stack, the call stack, to have very large growth, and we will not even be able to run it for very large values of n because the call stack usage and the processor usage becomes so large that it's just slow, and you don't want to run it like that. Base cases, we know that the index 0 and index 1 are 0 and 1. So those are two base cases that we'll use here. As I mentioned, we will also have to deal with stack overflow issues for larger values of n, and number overflow issues as well, because the size of the numbers becomes so large, these Fibonacci numbers, at a certain point that the long data type overflows and we'll need a BigInteger solution. And we provide an iterative alternate solution in this program as well. Looking at our code, we have a class called Fibonacci, a main method which instantiates the class, and then is going to call some functions in it to test various things. And here are some comments. Here's the test values for n that we're going to use, starting with 5 will be the first one we try. We'll change this when we're going to run it. And there's a note here, when you use 93 or greater, that's going to overflow along, and we'll have to use a BigInteger alternative at that point. And there's another note here, even for smaller values of n than 93, the usage of this call stack becomes of such a high order that you can't really practically run the program. It just outputs tons and tons of self calls. It takes up way too long. So we've restricted here for running the recursive Fibonacci. We'll only do it up through and including a value of 10. Anything larger than that, we will only be running the iterative solution. We'll be looking at each of these functions now: the recursive Fibonacci, the iterative Fibonacci, and the big integer Fibonacci. For each of them, there's an annotated version with an A and a non-annotated version that doesn't have the A on the end of it. Looking at the code, for the recursive Fibonacci, we'll bypass all the annotation code with the A's on the end and go right to the recursive Fibonacci, which is right here. It's not very much code there, as you can see. Only a few lines of code. It's an elegant solution to this seemingly complex problem. We pass in our index as an integer n. First we look for the base cases. If n is less than or equal to 1, 0 or 1 in our case, we're only going to pass in valid values. We're going to return n, because at 0 it's 0 and at 1 it's 1. Here's the general case. We'll have a long Fibonacci, and I'll scroll over so you can see this, and it will call itself in this one statement 2 times with smaller indexes, one with n minus 1 and then adding another call with n minus 2. Finally, when everything unwinds and the result comes back, we return the result. Let's now look at the iterative solution, the non-annotated one. Here's the iterative solution right here. If n is equal to 0, we return 0. Otherwise, we set up some longs here, a Fibonacci previous 2, which is 0, a Fibonacci previous 1 of 1, and a Fibonacci of 1. We have a for loop, an iterative, repetitive algorithm. We start our index at 2, and we're going to keep increasing it by 1 and go all the way up until n. And each time we're going to take the previous 2 plus previous 1, add them, and assign it as our new Fibonacci. And then we're going to change previous 2 to be previous 1 and previous 1 to be the current item. When that loop finishes, we return the long Fibonacci. For the big integer solution, the non-iterative one, is down here. It uses exactly the same iterative algorithm. The only difference is now we have big integer data types here, big integer 0 for the base case, big integer 0 and 1, and in this loop here we're using big integers, the add function, but otherwise it's the same algorithm. Alright, now we're going to start out testing this. We're going to start with 5, that's what it says here. We're going to test with first. Here's the output testing with 5, the 5th index, and we see that it's self-calling itself here. First to call to 5, then 4, 3, 2, 1, and then a base case of 1 is reached, and 1 returns a 1, and then a 0, base case of 0, and what's really happening here is there's quite a complex interaction with the calls because of those 2 calls that are occurring in each instance of the general case statement. So it's going all the way down one call chain, coming all the way back up, and then the other one coming all the way back up and adding it. So it's even quite difficult to follow here. You'd have to get a pencil and paper out and track each thing how it's working, but you can see it starts with 5 up there, it's working its way down, and there's various base cases, and at some point we have a 3, a 2, 1, and the 4 up here. It's quite a involved, recursive, intricate pattern that's going on there because of those 2 self-calls in the one statement. And the first call, it has to traverse it all the way back up the stack before it can do the add of the second one. So that's how that works. But the answer was 5. The iterative solution just calculates the numbers along the way here and shows them and comes up with a 5. So it's 0, 1, 1, 2. You can see the sequence unfolding there as it's adding previous two terms. You actually see the sequence there. The big integer solution is going to look just like the iterative one. Let's go to our next test value now. Our next test value will test one of the base cases, 0. And we see that it hits the base case, returns 0, and 0 is correctly returned. We'll move to the next test case. This test case, test 1, the other base case, and it returns 1 correctly on all the different versions of the algorithm. The next test case will be some simple cases. 2 and 3 will be next. Here's 2, and with the recursive you can see it has some self calls there, and down here for 2 it's 0 and 1 and 1, and finally 1 is the answer for index 2. The next test case will be 3. Here's 3, and its answer is 2. You can see it more clearly down here with the iterative. It's very easy to understand how that works. The recursive one is jumping all over the place because of the general case having two self calls. We'll go to our next test case. Here we're using the index 10, and note the recursive one. As we scroll down here, you can see as I'm scrolling down that there are many self calls. Just keep scrolling and scrolling and scrolling, scrolling and scrolling. Would not want to try to understand all that in my head. That would kind of, I'll let the computer figure all that out. That's one of the elegant things about these recursive solutions. We're just continuing to scroll, and you can see why we've limited this to 10. When you get to higher indexes, the order of magnitude grows very rapidly. The iterative solution on the other hand, for 10 is very small amount of output, and we see the sequence being built up there. Alright, we're going to go to our next test case now. For this test case, we entered 92, and remember that for anything bigger than 10, our code does not call the recursive solution because it's just too stack intensive. So we don't see the recursive solution here. We're going right to the iterative solution with n being 92. So it's building up all the way down here, and as we scroll down we see 92. We get the answer there, okay, and the big integer gives the same answer. But now we're going to go one index higher to 93 as our next test case. This time we're at 93, and when we scroll down the iterative solution, we see we have a problem here. The long type overflows, and the memory is interpreted as a long that's negative, which is obviously incorrect, and we cannot continue using the long type to get answers for values of the index 93 or greater. However, look at the big integer iterative solution for 93. As we scroll down, we do get an answer because it's not affected by any size restriction. This is our last test case that we're going to test. It uses an index of 100. The regular long iterative solution, of course, has problems after you get above 92. What's worse, of course, is the ones that don't look like negatives, because if you received an answer like that, how would you know if it was right or wrong? You might take that and use it when it's not correct. The bigger iterative solution, BigInteger iterative, does produce the correct answer for the Fibonacci number at index 100. So we'll go back now to the source code and summarize what we've learned here. We have demonstrated how to program Fibonacci numbers for the different indexes using a recursive solution and an iterative solution, and also touched on both issues in performance, in memory usage of the stack, in processor usage for this algorithm, the recursive algorithm, and also overflow issues of data types that caused us to have to use a BigInteger solution for some of those scenarios.